time we obviously started talking about equilibrium, and we talked about writing the equilibrium expression. Remember that the equilibrium expression is essentially products over reactants, and typically we use the concentration of the products over the concentration of the reactants. We also could use pressures as well, and if we have partial pressures of everybody, we could do the same thing, our products over reactants in terms of partial pressures. Remember, when we write the equilibrium expression, we could use the coefficients in the balance equation as the exponents when we do that. And when we calculate K, which is Kc when we use concentrations, or Kp when we're using pressures, it is just a number when we do solve for it. The number, as we talked about, does give us information about the reaction. It tells us, when we do reach equilibrium, would we mainly expect to have reactants or products present as a result of it? Again, a large value of K means we should mainly have products when we reach equilibrium. A small value of K means we should mainly have reactants when we reach equilibrium. And it's just a simple math of products divided by reactants. So large value means bigger products, right? More products, larger number. Small value of K means more reactants are present. So dividing by a larger number gives you a small number for K. We also talked about that you can go between the two. So in some cases, you may be given information about maybe pressures, so you could calculate Kp. Other times, you may be given information about concentrations, which would allow you to calculate the Kc. And we could use the formula that Kp equals Kc RT delta N to go from one to the other. In that case, remember, delta N is the number of gas molecules, and we do want to do products minus reactants when we do that. R is the gas constant, which is the 0.08206 number, and T is the temperature in Kelvin. So that allows us a nice way to go from Kp to Kc and vice versa. In reality, the numbers that you get for those values typically are not the same numerical value, but they do, again, give you the same information as to whether or not you mainly have reactants or products when you reach equilibrium. The other thing that we also talked about is essentially there's really only two things that we do include in the equilibrium expression, and those are things that have an aqueous symbol next to it and things that have a gas symbol next to it. Anything that is a solid or a pure liquid pretty much will not participate in equilibrium, and we do not include those things in the equilibrium expression when we do it. Any questions on any of that there? So I think last time this is where we laid up, yes, on this one? Yeah. So let's go through this one and sort of see what we got going on. So in this particular case, we are given really the pressures. So we have the pressures here. Thank you. And that means that we really want to look at Kp first for this particular reaction. So to write the Kp expression here, the Kp, if it writes maybe, you can do it, there you go. The Kp would be the partial pressure in this case of NH3 times the partial pressure of H2S, which is also a gas. And in this case, would we include this here? We wouldn't, as it is a solid, so we would not want to include it in our sort of Kp expression. That means this is essentially our Kp expression, which makes it relatively easy. We just got to plug that in twice there, 0.265 times 0.265. And in this particular case, we're going to end up with 0.0702 as our Kp value. First off, any questions on that part of it there? At this point, now that we have the Kp value, we can kind of convert it by using that other formula, which is the Kp is equal to our Kc RT delta N. In this case, we want to calculate the delta N. And in this case, our delta N would be, we have one gas molecule there and one there. So that is 2 minus 0, which should be a 2. And obviously R is the gas constant. And in this particular case here, our temperature is already in Kelvin, so we're good to go on that. So really you could just plop it in here. So our Kp, if you want to rearrange it, you can, or you can put it in. So it's basically 0.0702 would equal the Kc, 0.08206. Again, you can use 2.1 if you like. And this is going to be 295. And again, we want to square that part of it. So I'm going to take care of everything there on the right-hand side. So I'm going to take 0.08206, going to times it by 295. I'm then going to square it. If I can find my square on this, there it is. And if we sort of clean it up, we do end up with 0.0702 equals Kc, and we got something like 586.0127-ish. We're obviously going to then divide that to the other side. And in this case, we would end up with we'll call it 1.20. Is unhappy with the way I'm writing here. Try this again. 1.20 times 10, and that looks like 1, 2, 3, 4 minus 4 in that case there. And that obviously would be our Kc value in this particular case. Any questions on either of those? Now, in this particular case, would we mainly expect reactants or products to be present at equilibrium here? It would be reactants. Both of these K values, right, are small, which means we should expect mainly reactants at equilibrium. Again, remember, 1 is considered a large value, so anything above 1 is considered large. Anything less than that would be considered small. Any questions on that there? Okay. All right. All right, so the next thing we're going to talk about is sort of manipulating those equations, our equations. And sometimes we need to do this because not all reactions basically occur in a one-step process. So sometimes people think that pretty much all reactions is like reactants to products, and it really doesn't happen that way. There are a lot of reactions that basically occur in sort of multiple steps. Perhaps you probably don't remember because you didn't do it last semester, but there's something maybe you did previous to that, which is referred to as Hess's law. But basically the idea is we could take multiple reactions to get us to products. We can maybe do it in 2 reactions, 3 reactions. And it really doesn't matter sort of how many reactions we do, but we can add up all of our reactions. So if we take these 2 individual sort of reactions here, our A plus B goes to C plus D, which has an equilibrium constant, and then C plus D goes to E plus F. If we add these guys together, we can basically cancel out anything that is the same on opposite sides of the arrow. So we got a C on the left and a C on the right, so they cancel out. You kind of think of the arrow like an equal sign, like subtract it to the other side and it sort of cancels. Same thing here with our D. The D cancels out. And what this gives us is our overall reaction of A plus B goes to E plus F. Now, we could write our equilibrium expression for our first reaction, which is here. We could also write our equilibrium expression here for our second reaction, which is there. And if we write our equilibrium expression for the overall reaction, it is actually EF divided by A times B. So how do we get there? Well, we get there by basically multiplying. If we multiplied both of these K values together, C and D would cancel, right? And it would leave us E times F divided by A times B. So there are certain cases where you may have to manipulate an equation to figure out, like I want to know what the K value for this guy is. but I'm only given these two equations. And it may require you to add them together. When you add together an equation, what happens to the equilibrium constant is you then need to multiply the K values. So that's something different than you might think. The probably natural instinct would be I'll just add the K values together, but you actually need to multiply them together. If you added 3 reactions together, you would multiply all the K values for all 3 reactions, and that would give you the K value for the overall reaction. So that is one very common way that we manipulate sort of a reaction, is that we sometimes need to add them together to sort of find the K value for an unknown reaction if we're sort of given each of the steps along the way. Any questions on that there? Now, another thing that we sometimes will have to do is maybe if we look at this reaction here, and we have our K value, which happens to be this number, not important how we got the number, but obviously we get it by putting it into our equilibrium expression. But maybe we're interested in actually the reverse reaction, where the 2NO2 is the reactants and the N2O4 is the products. Basically, what we did as we went from left to right here is we reversed the reaction. And what happens to the equilibrium constant when you do that? It actually becomes 1 over the K value. So if you were to calculate the equilibrium constant for this reaction the way it's written, using this information, basically you would take 1 over the K value. So if you add up reactions together, you multiply the K values. If you need a reaction, but you need to actually reverse it, like the reactants need to be the products need to be reactants, you take 1 over the K value to calculate it. When we do see a K value, by the way, it is specific for how the reaction is written. So on the left-hand side there, the only correct K value would be 4.63 times 10 to the minus 3. It would not be what we see here, which was 200 and something, I think. It would not be 216. 216 value is specifically written for how that reaction is there, with the NO2 on the reactant side, the N2O4 on the product side. So when you see equations written and you see K values that go with it, it is specific for exactly how that reaction is written, and it's also specific for the actual temperature that is associated with that particular reaction. So this is another very common way that we manipulate equations, is we sometimes need to reverse them. When we reverse them, it basically affects the K value by taking 1 over the K value. Any questions on that there? Now, let's say we did have a reaction like A plus B goes to C plus D, and we have a K value. And if we wrote our expression like we saw on the previous page there, it would be C times D divided by A times B. But let's say, for example, we don't need 1 of everybody there, but we need 2 of everybody there. So if we were to take this equation and basically multiply it by 2 all the way across, we would end up with 2A plus 2B goes to 2C plus 2D. Now, how does that affect the equilibrium expression? The K for this equation would be the concentration of C, and it then would be squared, times the concentration of D, which would be squared, divided by the concentration of A squared and the concentration of B squared. So what we see here is if we need to take an equation and multiply by a common number, which sometimes happens, what it affects the K value here is, in this case, we multiplied by 2. We don't multiply the K value by 2, but we actually square it. If you multiplied the equation by 3, you would take the K value and cube it. So if you have to multiply by a common number, you multiply by a common number, you basically take the K to that number is basically what happens. Let's say we're doing the opposite here and we're going from this guy back here to the first equation. If I went from the second equation back to the first equation, I essentially divided everybody by 2, right? What happens to the k value if we're going this way? Because I divided by 2, the k value actually is the square root of the original k value. If you had to divide everybody by 3, you would take the cubed root. So if you have to divide an equation by a number, you basically take the k value, the root of it, to whatever that number is. So again, if you divided by 3, you would take the cubed root. Divided by 4, take the 4th root. And if you divide by 2, you would obviously take the square root. So those are very common ways that we manipulate these equations to really in a situation where you're sort of given an overall equation, but you're not really given the k value, but you're given kind of individual reactions or equations that you could use to sort of figure it out. Any questions on any of those sort of manipulations there? Here. So let's say, for example, we had a plus b goes to c plus d. Now let's just say the k value is 5. And let's say we have c plus d, like we got up there, goes to e plus f. And we'll just say the k value is, we'll go 6, just make up a number, why not? So let's say we wanted to figure out what the, k value would be. Let me see here. Actually, we'll do it this way. We'll make it like this. There we go. Let's say we wanted to figure out what the k value would be for this reaction. 2e plus 2f goes to a plus b. So why don't you take a second and see what you come up with. All right, so let's take a look. So in this situation, this is sort of your goal. You basically want to build this equation, basically using the other equations that are there. Really, the simplest approach is to kind of just start with one thing and make sure it's on the correct side and you make sure you have the right amount. So for example, here, if I look at A, I can see I need one A and I also need one B, but it is on the opposite side, right? So instead of reactants here, I do need it on our product side, which means to this first equation, we need to really reverse it. So what we would do is we would take 2C plus 2D gives us A plus B. When I reverse that reaction, what happens to the K value? It becomes, yeah, so the K value here becomes 1 over the original number, which is 1 over 5 in this case. That then takes care really of this equation. When I look at the next equation, I see that in this particular case, the E and the F is also on the wrong side, which means I do need to reverse it. In addition, though, I need how many E's and F's? I need 2, which means in addition to reversing this guy, I got to also multiply it by 2 and reverse it, right? So when I do that, that would give me 2E plus 2F, again, reversing it and multiplying it by 2, goes to 2C plus 2D. Now we got to kind of keep track of what we did there. We reversed it, which means the K would be obviously 1 over the 6, right? But we also multiplied it by 2, which means we also need to square, if I get it in there, square the 6 as well, right? Because we multiplied it by 2, which means if we add this together correctly, everything on the left-hand side and right-hand side that are the same could cancel out or reduce down. In this case, I got 2 C's on the left and 2 on the right, so they cancel. I got 2 D's on the left and 2 D's on the right, which cancel. And if I did this correctly, everybody on the left stays on the left. So that's 2E plus 2F goes to A plus B, which means, did I hit what I'm looking for? I did. In this case, we then need to basically multiply these K values together. So basically, we're taking, for our K, it would equal 1 divided by 5, which looks like you get a 0.2. And we're going to basically square it, which would give us 6 times 6, which should be 36. And then we also need to take 1 divided by 36 because we reversed it as well. And that would get us something in the ballpark of 0.0277, bunch of sevens all the way across. We then want to, again, not add here, but we want to multiply these two values together. And if we do that, it's looking like perhaps we end up with a K value here for the overall guy. And we'll call it 5.6 times 10, 1, 2, 3, minus 3 in this particular example here. Are probably, since there's all 1 sig figs on everybody else, 6 times 10 to the minus 3 would probably work in that particular case. Any questions on that there? So the key is really just to start with one thing, make sure you get on the correct side, make sure you have the right amount. And really the other key is you got to just kind of keep track of what you did to the equations so that you then can manipulate the K values and then multiply them together. Any questions? Yeah. There's no real name for this per se, but it's very similar. Again, they kind of take it out of 200A. You don't do it in 200A. We do it in here. But there's something known as Hess's law where it's kind of similar to that, except Hess's law deals with energy and delta H, and you actually add the delta H's together. So it's similar to that, you know. But it's the idea that not all reactions basically happen in sort of a one-step process. Very common, lots of reactions occur in multiple steps along the way. And sometimes we do need to sort of build the reaction we're looking for through the use of other individual ones. Other questions? What's that? Oh, no. So something that's very similar to this, again, a little different because obviously these equilibrium constants is what's known as Hess's law. And that's where you take delta H's and you basically build a whole bunch of individual reactions, put them together. But it's really different in terms of how you manipulate the delta H value. In that case, you multiply by 2, you would times it by 2. But here with the equilibrium constant, we actually square it and things like that. So it's a little bit different. But the application is very similar in terms of building the overall reaction. Any questions on that there? Yeah. Yeah, so it would be a problem very much like what I wrote here. You know, you would have sort of a desired equation, something you're looking to figure out what the K value is, and you're not given, like, for example, individual concentrations or anything like that, but you're given several individual sort of equations that have K values. Then you would want to sort of build it and calculate that way. Yeah, so the idea when you reverse a reaction, it basically becomes 1 over K. Because really what we do, right, is we take products divided by reactants normally. So when you reverse a reaction, your products become your reactants become your products, so the whole thing flips, basically, is what happens. Other questions? Okay. All right, so let's go this way here. So as I mentioned, as we saw here, again, typically when we write the equilibrium expression, we want to leave out anything that's a solid or a liquid. It is just a number, and typically we write our Kc, our Kp value, depending if you got obviously concentrations or pressures. As we talked about last time, obviously to do a Kp, you need gases, right? So if you got no gases there, like we saw, I think in the example earlier, you obviously cannot write a Kp value. Again, no liquids or solids, as their concentrations really don't change in terms of liquids, and solids really aren't participating. No units associated with K, which is a good thing. And as I said before, when you do see a K value, it is very specific for the actual equation that you're looking at, exactly the way it's written. Obviously, if you flip the equation around, you need to manipulate the K value for the flipped around equation if you should do that. As we just saw there, obviously, if we add more than one reaction together, and it can be 2, 3, 4 reactions, however many reactions, we do multiply all the K values together. And again, the couple of other sort of manipulations as we just talked about, if we reverse it, 1 over K, if you multiply by a common number, you take the K value to that common number. Like, for example, we did the squaring there, so we did by 2, so we squared it. Again, if you did 3, you would cube it. And obviously, if you divide by a common number, you take the root value of K to that common number. Now, K, as we also talked about and touched upon last time, is a constant value as long as the temperature doesn't change. And as we touched upon last time, that means, in a reaction, if you started with different amounts of reactants each time, it should still come to equilibrium as long as the temperature doesn't change to the same ratio of products to reactants. Even if you start with a little bit of everybody, some reactants, some products kind of tossed in there, when it comes to equilibrium, you should end up with the same value of K. It doesn't matter how much you're starting with in each reaction. Really, the only thing that matters is you don't change the temperature. It will always come to rest at the same amount. So again, that's something that's sometimes hard for people to understand. They sometimes think, well, if I started with a lot more in this run, my K value should be a lot different, or if I started with a lot less, or I had a little reactants and products. But again, it's really only the temperature that can affect it. So as long as that doesn't change, it doesn't matter what you start with in terms of the reaction, you should end up with the same ratio of products to reactants. Yeah. Say, will it won't change the K value if you're asking, if you had, if you had a reaction where there was coefficients of 3, 4, whatever it may be, it would be specific for that individual reaction. So whatever their coefficients are, it will come to rest at a certain value for the equilibrium constant. And again, it doesn't matter if the coefficients aren't 1 or 3. If you throw in as much as you want reactants or products, as long as you don't change the temperature, even if the coefficients aren't 1 or whatever the numbers may be, it will always come to rest at the same sort of ratio of products to reactants. Now, you may, if you're comparing that to a different reaction, obviously they would have different K values, again, because the K values are specific for the reaction you're looking at. Other questions? Okay. So the next thing we're going to talk about is another letter to break up the K, but we're going to talk about Q. Q is the reaction quotient, and the good news is we calculate Q the exact same way as we calculate K. So Q is calculated the exact same way. It is the concentration of the products, again to the exponents, divided by the concentration of the reactants. And again, like I said, you take the coefficients, you use those as your exponents, just like we calculate K. So you may be saying to yourself, if it's calculated the same way, what's the deal with K? Why is it important? Well, Q is calculated here to determine whether or not you are necessarily at equilibrium. So you may be given some concentrations of everybody, reactants, products, and you may want to determine, hey, am I at equilibrium or not? It may not tell you like, hey, you're at equilibrium. So a basic Q problem is to determine basically two things. The first thing is, are you at equilibrium? And the second thing is, if you are not at equilibrium, which way do you need to go to reach equilibrium? Do you need to make more products? Do you need to make more reactants to get to equilibrium? So that's sort of your basic run-of-the-mill Q problem. We will see Q a little bit later on in another application, but a lot of times that is the situation. Obviously, in order to calculate Q, you need to have the concentrations of everybody, reactants, products, basically to do that. Obviously, if you're not given concentrations of products, there's no way you can calculate Q. So if you come across a problem, that's a really big hint that either it is like a Q problem or you should calculate Q, is if you're given a problem, they do not mention like these are equilibrium concentrations, but they give you concentrations of everybody in the reaction, you should calculate Q. That's basically what you should do. And again, the other type of question would be just a straight, it is a Q problem. So what do we do with the Q? Well, we calculate Q and we compare it to the K value. And if you can calculate Q and it is greater than the K value, basically what that tells you is you are not at equilibrium. And in order to reach equilibrium, you need to go towards the reactants. So I look at it like this, opposite of where it's pointing. If you think about a reaction, there's reactants and products, right? So it has to go to the left. It has to make more reactants, basically, to reach equilibrium. If you happen to calculate Q and it actually does equal the equilibrium constant, congratulations, you're at equilibrium at that point. You basically have hit that point where the rate of the forward reaction equals the rate of the reverse reaction. If you calculate Q and it does not equal equilibrium, or Q is less than K, then it is not at equilibrium, and to reach equilibrium, you need to make more products. So we could calculate Q using concentrations is typically what we do. You could technically calculate Q with pressures and compare it to the Kp value if you have it. So like I said, there's basically two types of problems. One is just a straight Q problem where it basically asks you that question, are you at equilibrium? And if not, which way you need to go. And secondly, we'll see a little bit later on that you should calculate Q in a certain situation when you are given all of the reactants and products sort of information. So we kind of use it as like an initial calculation. If we're not sure we're at equilibrium, it will help us decide if we have reached equilibrium. Any questions on that there? Yeah. No, so in the last situation, like you're talking about here, if Q is less than K, it tells you first off you're not at equilibrium. In order to make equilibrium, you don't necessarily have to add more products, but you do need to kind of shift to the product side or start making more products in order to reach equilibrium. So you need to kind of build up the products, which you could technically toss in if you wanted to, or it just needs to kind of work its way to the product side until it eventually will reach equilibrium and stuff like that. Yeah. Other questions? All right, so why don't we try one here, see how it goes. If you start with a reaction and there's 0.249 moles of N2, 3.21 times 10 to the minus 2 moles of H2, and some NH3 in a 3.5 liter vessel, and the Kc is 1.2, is the system at equilibrium? And if not, which way do you need to go to reach equilibrium? Take a couple minutes, see what you come up with here. So in this particular case, we are given really the concentration to everybody. It is sort of in parts, if you will, but remember molarity. Molarity is moles per liter. We do have the moles and the liters of each of these things. So we could calculate the concentration and the molarity of each of our guys. So the concentration of N2 would be the moles, which is 0.249, divided by our liters, which is 3.5 liters. And it looks like for N2, we get something like 0.0711 molar. We could also do it for our H2, and our H2 would be our moles of H2, which is 3.21, it looks like, times 10 to the minus 2, divided by our 3.50 liters as well. And it looks like 0.00917 on that. And lastly, we obviously could do it for our NH3, which would be 6.42 times 10 to the minus 4 moles, divided by the 3.50 liters. And it looks like we hit something like 0.000183 molar for that guy. Any questions on calculating that there? What we do see is a basic Q problem here, which is we are given the concentrations of everybody, which means we can calculate Q. Q is calculated the exact same way as we would calculate our K. So we would take the concentration of NH3. We would need to square it because of the coefficient that's here. We would then need to divide it by the concentration of N2 and the concentration of H2. And obviously, we do want to cube it in that case. Any questions so far? All right, so we're going to plug this in. I'm going to swap a page here, I think. Go this way. There we go. So putting that in, our Q would equal our NH3, which looks like it is 0.00, hopefully not missing a 0 here. And that did need to be squared, divided by our N2, which was 0.0711, and our H2, which was 0.00917, and this guy needed to be cubed. And if you do that here, we get 0.00, 183 squared divided by our 0.00917 cubed and divided by our 0.0711. Looks like I missed a zero. We'll try that one more time here. 0.000183 squared. Let's find my real calculator one of these days. 0.00917 cubed and divided by 0.0711. There we go. 0.611 looks like our Q value in this particular case. Any questions up to there? Now our K value in this case was 1.2. So at this point, we want to compare Q to K. Q in this case is less than K, which that first tells us, are we at equilibrium? Yeah, we're not at equilibrium. And in order to reach equilibrium, we need to make more reactants or products. Yeah, so go opposite where it points. So towards the product side, there is what we need to make. Any questions on that calculation there? This is what I would call just a straight old Q type problem. And it is a question like this, like, you know, you're given concentrations or something like that or pressures, and it asks you basically, are you at equilibrium and which way you need to go. Later on, when we talk about in just a second or so here, talking about calculating equilibrium concentrations, you sometimes do need to calculate Q to determine which way the reaction is going. And that's another place where you might need to calculate Q. Again, a reminder, you cannot calculate Q if you're not given everybody's information. So that's a good way to know if you can or not sort of calculate Q. If you definitely are not given everybody's information, you definitely cannot calculate it. Any questions? Wow. It was like 90 the other day, right? All right. So let's talk about actually solving equilibrium problems. So in not all cases will we be given, you know, equilibrium concentrations. And sometimes we may be asked to actually calculate the equilibrium concentrations. And we're starting with initial concentrations to do that in most cases. So this is really sort of the calculation of the class here. The way that we calculate equilibrium concentrations or even equilibrium pressures is we really want to leave kind of like only one unknown, right? And it's a lot easier, obviously, in math if you have one unknown. And that's the goal here. And the unknown that we usually solve for is X. And X really represents, as it says here, the change. And the way that we approach these problems is we typically do what are referred to as ICE tables. Wow. And I stands for initial, change, and E means equilibrium. So initial, change, and equilibrium is an ICE table. You may be familiar with ICE tables. If you took me, you should be familiar with ICE tables. You maybe did it when you did limiting reagent type problems. It's kind of the same deal, very similar to that. But we use these tables basically to help us calculate equilibrium concentrations where all we're given is basically initial type concentrations. So how does this work? Well, say you have a reaction like 2A plus 2B goes to C or something like that. Now, if we have a K value of like 120, for example, and let's just say initially, in terms of the concentration of A, we have 2 molar, and the concentration of B, we have 4 molar in this particular case. We would do an ICE table like so. We would take our initial concentrations here and basically put them in. So this would be 2. This would be 4. And in a lot of problems that you come across, you're really not given any information about the products. And if that is the case, you could always very safely put 0 there to start with for our equilibrium, our product side. Now, the change part is really the important part here. The change part is what we're ultimately solving for. Now, if we have no products to begin with in this particular case, we could probably safely assume this reaction is heading in which direction? Yeah, it's probably safely heading towards the product side, as we don't have any products, so obviously we can make some products to do that. Which means as time goes on, would we expect to have more or less reactants? To have less, and we represent less by basically subtracting. So we're going to subtract our reactants. We also should expect, because the reaction is heading to the product side, we should be making more products, which means we should end up with pluses, our positive side, on our product side. So the change part here would be minus 2x, and plus x. Now you may be wondering where the x comes from, the 2 comes from. It is the coefficients. It is super important when you do the change part in the ICE table that you take the coefficients into account. And the reason that is that's really the stoichiometry. That's the mole-to-mole relationship. You are doing the mole-to-mole relationship when you take the coefficients into account. And if you remember when we did it for limiting reagents, that basically took care of doing the mole-to-mole relationship basically for you. Any questions on that so far? At this point, basically for our equilibrium, we're just going to simply carry everybody down. So this would be 2 minus 2x. This would be 4 minus 2x. And this would be x. Now, what we want to do at this point is actually solve for x. And to do that, we would use the equilibrium expression to do so. The K in this case would be the concentration of C divided by A squared and B squared, and that would equal, in my made-up example here, $1.20. At this point, we would take all these guys here at equilibrium, and we would put it into this expression, and you would solve for x at this point. I won't do it because that's a crazy math I just made up here, so we won't do this one. But you're basically going to solve for x. When you do solve for x, that is not the equilibrium concentrations necessarily, but it is the change part of the table. So once you solve for x, what you would do is you would take that x, and that would be every single x that you see in the table, and that will allow you to figure out the equilibrium concentration basically of everybody that is there. Any questions sort of on those steps there? Yeah. It wouldn't be 0 because we don't know what x is. So even though it's like 2 minus 2x, unless x is 1, it won't cancel out, right? So that's when you solve for x. It probably won't cancel out. It might, but we don't know. It's not really 2. So it's really 2 times something. And that 2 is really the mole-to-mole relationship, because mole-to-mole, right, this is 2 moles of A, react with 2 moles of B, gives us 1 mole of C. And that's really what that 2 is for that mole-to-mole relationship. Yeah. What's that? You won't have the x. You actually have to solve mathematically for the x. And at the end of the problem, you will have the x that you then would go and put back in. And that, let's just say, for example, I don't know, the x here was 0.5, right? And that first one, what that would mean is you would figure out the concentration of A was 2 minus 2 times 0.5. So it would come up to like 1 in terms of the concentration would be the equilibrium concentration. So you will do the ICE table. You'll then solve for x, and then you can put the x back in to do it. Any questions on it? Yeah. So it's math in a sense, yeah. So it is math, and we're going to go through some different examples of different ways that you could solve for it. The most complicated math that we will do in here, to keep it simple-ish, is the quadratic sort of equation, quadratic formula. So maybe you're familiar with that, and that is x is equal to minus b plus or minus the square root of b squared minus 4ac, yeah, divided by 2a. I have like a mind froze right there. And that's based off of ax squared, right, plus bx plus c equals 0. Yeah. So this is something that we definitely will use this equation a lot to solve some of them. And this will be pretty much the most complicated way to solve it. There are some other ways you'll be able to solve some of these, and we're going to go through some different examples and show you when to sort of apply those other ways and when you should not apply the other ways. I'm sorry, we'll get you first. Yeah. Yeah. No, it's just, we're just bringing everything down so that we can then take it and put it into the equilibrium expression and solve for x. So this guy over here. So for C, we would put in there, all right. So if we were to solve this, we're not because it's kind of crazy, but basically we would take the x, which is our C, right? We would then divide it by 2.0 minus 2x. And I ran out of room, but times that on the bottom by 4 minus 2x. And that would all equal the 120. You got to solve for x. Got it? Right up here? Yeah, I'm sorry. Yeah, so you would then have to solve for x, do some foiling and all that, whatever they call it, making turkey, you know, factoring, labeling, solve for x, bring everybody to one side, and all that good, fun, terrible math. Yes. It'll be situations where you do end up, when you go to solve for and kind of combine everything, you end up with an equation that looks like that. Like you got x squared plus x plus a number and stuff like that. Yeah. Is there another question? Yeah. Yeah. When do I put, I'm sorry, say again? Yeah. So when you solve for x, what the x represents is a change, and it's the x value in each of the equilibrium concentrations. So you would put the actual number in there and solve for the actual concentration. All right, why don't we do one together with real numbers, and we'll kind of see how it goes, okay? All right, let's take a look here. All right, we're going to look at this equation here, or this problem. At 1260 degrees Celsius, not really important. The equilibrium constant for the following reaction is 7. If the initial concentrations of Br2 is 0.663, we want to calculate everybody's equilibrium concentrations. So first off, we could start with our equilibrium expression. So in this case, K would equal our products, right? Which in this case is Br, and we do need to square it because of the coefficient that we see. And that would be divided by the concentration of Br2, and that would equal our good number of 7 right there, which hopefully I'll be happy with in a second. I made it up years ago, we'll see. At this point, we now want to go into our ICE table. We're really only given information about our reactants. So personally, I'm just going to rewrite the equation here so I could do my ICE table. So initially here, this guy is going to be 0.663. Like the other example, we're not given any information about our product, so it's fairly safe to assume that this reaction is going to start with 0 amount of product. Any question on the initial line there? It is, unless they give you product, yeah? So if they don't give you any information about the product, it's pretty safe to assume that it's 0. And it's also pretty safe to assume that we should have this reaction heading, like we talked about, towards the product side in this case, right? So that tells us when we get to the next part of our ICE table, which is the change part, we should expect our reactants to decrease with time, and we should expect our products to increase with time, right? Because it is heading towards the products. Here in the change part, we're going to do minus x because it should be decreasing. Coefficient on the Br2 is 1, which is why it's just minus x, basically 1x. Coefficient on the Br is 2, and it's a product, so this would then become 2x. Any questions on the change part? Because of the coefficient, yeah. And that is critically important because if you do not use the coefficient, you essentially didn't do the right stoichiometry. Like you talked about in 200A, you got the wrong mole-to-mole relationship and everything's not going to come out correct. Now, when we get to the equilibrium line, we're just going to simply carry everything down here. So on our equilibrium, we would have 0.663 minus x, and this would just be 2x. Any questions on that so far? Yeah. Yeah, so the idea here is we could safely assume, because we're not given any products, that this reaction should be going in the forward direction. Yeah? Which means we should be making products, right, in this case. That means as this reaction goes through, in order to make products, you have to use reactants, which means the amount of reactions should start to go down, and the amount of products should start to increase because of the direction the reaction is happening. If you remember early on, we saw like a curve, right, where at the start it was all reactants, right, and they went down, and then we had no products, and then the products started going up. And that's basically what's happening here. Because we're assuming the reaction is going to the product side, we need to be increasing products because we're making it. But in order to do that, you have to use up the reactants. And that's why the reactants in this case is negative or minus, because we're losing them and we're making more products, and that's why they're positive. Other questions? All right, so now is the math part. We're going to take everything that we have on the equilibrium line, and we're going to actually put those values into our equilibrium expression here. So if we do that, up on top should go 2x, and we should square it, right, because of that square right there. And on the bottom should go 0.663 minus x, and that will equal 7, which is the equilibrium constant value in this particular case. Any questions on that there? All right, now we got to do some math. So math-wise, we should do what with the stuff on the bottom there? We should multiply it to the other side. So we're going to basically multiply whatever's on the bottom to the other side. By the way, I'm also going to square the top there. So that should give me, that should give me 4x squared is equal to, there it is. All right. Shit. Let's just hope for some electricity to go out. No, I'm just kidding. That's wrong. That's right. 0.663 times 7. That gives me 4.641 minus 7x. So again, all I did was squared the top, multiplied the bottom to the other side. Yes, sir. Because of this, and because of the expression, and mostly because of the coefficient. Yeah. Other questions on that? Now, this, as I think an earlier question was asked, is this is really shaping up to be a quadratic sort of formula type deal. We got x squared, we got x, and all that. So when we do this, we really want to bring everybody to one side and equal it to 0. You don't have to do this, but most of the time, most people will keep the x squared guy positive and kind of move everybody to that side. So I'm going to move everybody here to the left-hand side. That would give me 4x squared plus 7x, and that would be minus 4.641 would equal 0. So again, basically, I moved everybody back this way to that side to set it equal to 0. Any questions up to there? At this point, you look at this and go, sad, because now I got a quadratic, unless you like the quadratic. But you do need to do this. By the way, this a value, ax squared plus bx plus c is equal to 0 is what we're looking at here. That means in this case, a is equal to 4, b is equal to 7, and c, you do keep the negative 4.641. Yeah. We're going to put that into our quadratic formula, which I wrote there on the other page. X is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. And for good practice, why don't you solve for what x equals? By the way, when you use the quadratic formula, how many x values do you get? You get 2. So why don't you take a second, put the numbers in and see what you come up with. And then we'll continue on and make sure everybody at least gets a little practice here with the quadratic. Yeah. Yeah, you'll probably know it by the time we get there, but yeah, it's something you should know. It won't be provided to you, yeah. But you'll have to, unfortunately, use it in a number of problems. Yeah. Okay, let's take a look at this before we do lose power here, maybe. All right, so we're going to, again, put our A, B, and C into there, and let me flip a page, I think. Let's do this here. All right, so putting it into there, our x will equal our minus b, which in this case is minus 7, I believe, plus or minus the square root. Again, if you put all the numbers in there and kind of clean it up inside the square root, you should get like a 123.256, which then you would take the square root of and end up with 11.1 when you do the square root of it. And that would all be divided by 2 times a, which is 4 times 2, which would be 8. So again, if you did the b squared minus 4ac, you should get 123.256. Inside the square root, obviously you need to take the square root of it, and that gets you to your 11.1. Any questions on that there? Now, again, we do get 2 answers in this case. So that is going to be our first one, which would be minus 7 plus 11.1 divided by 8. And I believe that will get you a 0.5125. Your other option would be minus 7 minus 11.1 divided by 8. Gives you a negative 2.2625. Any questions on the 2x answers here? Now, when you do the quadratic and you get 2 x values here, one of them will make sense and one of them will not make sense. So I'm just going to recopy the equilibrium part of our table. And I believe in the equilibrium part of our table there, we had 0.663 minus x, and that was for, oops, come back here. That was for BR2. And over here we had BR, and that was, I believe, just 2x at that point. So that is 2x at that point. Now, in this particular case, the one that would not make sense is the negative one, right? If you put that negative back into 2x, you end up with a negative concentration, which you cannot have. So one of the cases when you use quadratic, one of them will not make sense. One of the answers, when you put it back in for x, will give you a negative number, and that's obviously not the right one. Now, you may be asking yourself, isn't it always the negative number? Well, the answer is no. You could get an x value that's both positive, both negative, one positive, one negative. So you do need to kind of think about it sometimes. Sometimes like this one is pretty obvious. Obviously, the negative one is going to be the one that's not going to work. So what that means is this is the correct x value here for us. We're now going to go back to our equilibrium table and put it in for each of them. And that means that the concentration of BR2 would equal 0.663 minus our x value, which is 0.5125. And that gives us a BR2 value of, we'll call it 0.151 molar. It does need molar since it is a concentration. If we go into our BR, it is equal to 2 times x, which would be 2 times 0.5125. And that gives us maybe like a 1.03 molar for our Br concentration. These would be our equilibrium concentrations for each of these guys by taking our X value, obviously, and substituting it in to our equilibrium line. Question on that there. Now, it is math, which means math is good in a sense because let's say we screwed up on the math along the way or not sure if we screwed up. How can we check to see if we did okay? Any ideas? Yeah, so since these are now the equilibrium concentrations, we could plug it into our equilibrium expression. If I could get it to stop doing that, maybe. There we go. Maybe not. And this was our BR squared. So we take our 1.03 squared, and I believe it was divided by just BR2, which would be our 0.151. And if we do all that good stuff there, 1.03 squared divided by 0.151, I get an equilibrium constant about 7.02, which is pretty close to the 7 that we started with. If you plug it back in and you get like 142, clearly math-wise you went wrong somewhere along the way. So it's really a good idea to put it back in and check it. And it won't come exact all the times, but it should be really close. Obviously, with rounding, you might be a little bit off, but you definitely should be in the same ballpark as your original K value. And that's one of the nice things about math is you can kind of check yourself to make sure you didn't do anything incorrect. Questions on any of that? Yeah. Yeah. It was asking for the concentrations of everybody at equilibrium, I believe, if I'm not mistaken. Yeah. Calculate the concentration of all these species at equilibrium. Yeah. Now, one last thing here before we wrap it up here for today is we talked about Q, right? And in this particular case, you could not calculate Q because you were not initially given products, right? But you could calculate Q if you were, and there could be problems where you're given concentrations of everybody. We would calculate Q, and what it would help us with is the change part. So let's just say, for example, we calculated Q, and it said you're not at equilibrium, but to reach equilibrium, you actually need to go make more reactants. What would that affect on the change part? Yeah, so it would be going in this direction if that was the case, right? Which means this side actually would be negative and this side would be positive. So in a rare case, and it does happen occasionally that you are given sort of a ice table problem like this, and you are given the concentrations of everybody, you should quickly calculate Q just to make sure you're not actually heading in the opposite direction based on your assumption. Probably 98% of the time, 97% of the time, you can almost no-brain in and go, it's going to go that way to the products, but there are certain situations where it might not do it, and it might actually go the opposite way. Any questions on that there? Yeah. You could actually just flop the signs and use the K that's there. Yeah. And it will come out. Or you could do the reciprocal and then you would flip it around. So you could actually do it either way, but you could just flop the signs and it actually work out okay. How did I get? I say it one more. How did I go with? On the next slide. Yeah. So. Oh, I went with. So these were the two X values that we came up with. And every time you get two X values, one of them will not make sense. So let's just say, for example, I felt it was this guy that I crossed out. When I would put it into this 2x, right? It would basically be 2 times the minus 2.26, whatever it is, 25. Basically giving us like a -4 molar. You can't have a negative concentration. So it doesn't make sense, which is why we can't use that one. So that's why we chose that one, because when we put it in there, it's actually less than this, which makes sense. And it won't give you a negative, and then obviously it works okay on this side as well. So you will always run into that situation when you use the quadratic. You always get two values. One of them will not make sense when you go put it back into the equilibrium line. And really how it won't make sense is it will lead you to a negative number, and you can't have a negative number. It's a good thing to remember for a lot of calculations, yeah. then probably something went wrong. Yeah. So, but you can definitely get two negatives in certain cases. You can get two positives, and obviously you can get a positive, negative. But it's really the part where you put those numbers back into the equilibrium line. One of them probably will lead you. It should lead you to a negative number, which obviously is the wrong one to use. Other questions? Yep. All right, let's lay it up here today. We're starting on equilibrium and lab.